So when we're talking about single subject analysis, or really more properly, first level analysis, what we're talking about is taking every single voxel inside in the run and looking at its time series. For example, we could take this voxel right here in frontal cortex, looking at the time series and then asking, is the variance in this voxel explained to some extent by the paradigm? In this case, is sort of these big blocks. In other words, does the squiggles in this voxel, do the ups and downs in this voxel, the time series of this voxel, do they seem to be attributable to the onset and offset of some task of interest? Then maybe we'll take another voxel and it looks more like this, and maybe another voxel and it looks more like this. So we're going to repeat for every single voxel inside the brain this analysis. And there's one thing that I want to point out, and maybe it's obvious to you and you already know it well, but it's important to keep this in mind. Anytime you do statistical analysis, there typically are two components. On the one hand, you're trying to estimate an effect. You're trying to estimate what is the magnitude of the effect of a certain task on each voxel of the brain. In other words, you're estimating the regression parameters beta. And that's one part of the analysis. The other part is the inference. So that means assessing whether the effect that you have estimated is statistically meaningful. And now the reason why I mentioned that you should keep these two aspects of the analysis separate is because it frees you to think about integrating different strategies for each step. Typically, we're all used to doing, for example, a GLM and then a t-test on the parameters. This is sort of the most conventional thing you could do, and it is what we will be doing in this course. However, keeping in mind that these two are separate things means that you could do a GLM first, and then you could do an unparametric test for the inference. Or maybe you could do an estimation. You could run a regression first on every single voxel, and then don't even do an inference on a single voxel, but do a multivariate inference where you look at the pattern of voxels within certain areas. Okay, so I make this distinction so that you can keep in mind that you can use multiple strategies for the analysis, not just a conventional approach. Now, for estimation, we're going to use a conventional approach, the general linear model. And as you know well, there are several different ways of estimating a parameter beta within this framework. There is the weighted least squares, the generalized least squares, a smoothing approach, a sandwich approach. We're going to start with really the most basic one, which you're probably very familiar with, which is the ordinary least squares, which is written down here, but simply put is the idea of finding, as in any regression, what is the relationship between an independent variable x and a dependent variable y. In visual terms, what you're doing is you're trying to find what's the best line, what is the line that best fits these data. So is it this one, or is it this one, or is it this one? Now, more formally, the way in which we do this is by minimizing the sum of the squared error. In other words, the sum of squares of the difference between the actual observations that we have and our prediction, i.e. our line. Right, so to give an example, in order to calculate the sum of squares, we would take every observation, subtract it from our prediction, square that up, then we take the next observation, subtract it from our prediction, square it up, add them. Then we take this other prediction, subtract it from our, we would take this observation, subtract it from our prediction, square it up, add it to the previous, et cetera, et cetera. We would do this for every single point. And so we would calculate the sum of squared error, the sum of squares for the error. And then you move the line a little bit and you repeat the same thing. And eventually you pick the line that gives you the smallest sum of squares, right? In a visual sense, that's what we're trying to do. Now, the example I gave you is a so-called simple linear regression, where we had one independent variable and one dependent variable. But in the context of fMRI, that is rarely the case. Usually, we are talking about a multiple linear regression, something that might look something like this. So we're trying to predict our variable of interest y, which is nothing but the time series of the voxels. In fact, I show it here. We're trying to predict the time series of a voxel. So y, the vector y, is the series of values that are taken by a single voxel over time. So this is the value in voxel 1 at time point 1, voxel 1 time point 2, time point 3, time point n. And we're trying to predict this with a number of regressors, or independent variables, which typically some of them code the onset and offset of our conditions of interest. And this matrix could also have in it some regressors of non-interest, or some covariates. Then, of course, we have our vector of parameters, which is what we're trying to estimate. And then we have residuals. Let me show you sort of, so typically if you read articles or books that explain this, you will usually find this collapsed into matrix notation, which is what you're seeing here. So sort of the column vector y equals X matrix times the vector of parameters plus error. But let me show this in a different way, which might be more helpful. So, or rather might make it a little bit more concrete. So this is our regression, right? And so y, as I said, is nothing but the time series of one single voxel. So we're going to repeat this analysis at every single voxel, which is also why fMRI analyses are often referred to as a massive univariate analysis, meaning we do a massive number of univariate analysis, one per voxel. So as I was saying, our vector y is nothing but the time series of a single voxel for one given run. And then our design matrix, or the X matrix, usually has a number of regressors of interest. So these are the events that are part of my experiment. For example, maybe condition 1 was off, then there was a trial here for condition 1, and there was a trial here for condition 1, then nothing, then another trial, et cetera, et cetera. Condition 2, on the other hand, happened sort of at these points, and here's condition 3. So these are my 3 regressors of interest. Now, there might be, as I was saying earlier, a number of regressors of non-interest, also typically referred to as nuisance regressors. In fact, if you are interested in resting state, usually you're doing this type of regression only with nuisance regressors, so that after you can take the residuals and run some interesting resting state analysis on that. In our case, we have some regressors of interest, since this is a task-based analysis. And then we have a number of nuisance regressors. Most typically, we might have 6 motion regressors, and perhaps a high-pass filter. Right? So this is a slow drift meant to capture and explain away any slow drift into that. And then we have our parameter vector. And the parameter, as you know, is simply saying the amplitude of each, or the degree to which a change in each of these regressors of interest or non-interest is associated with a change in the degree to which a unitary change, in the regressors of interest is associated with a change in the dependent variable. And so, of course, we have, for example, in this case, beta 1 obviously is the parameter associated to regressor 1. Beta 2 is the parameter associated to regressor 2. Beta 3 is the parameter associated to regressor 3, and so on and so forth, down to the very last parameter p. So in a sense, you can think of this a bit like baking a cake. We're trying to find how much of each of these ingredients do we need, and in what combination, in order to best predict y. Okay, so essentially that's what the estimation part of this is. We're trying to find out just how much of each of these ingredients do we need in order to approximate as well as possible y. And then, of course, there's an error term. So how do we calculate beta? Well, it'll be tempting to just say, well, we just take the x, we can invert it on the other side, and then our beta is nothing but x inverse y. But of course, you might realize that x, as you saw from the previous slide, is not a square matrix, so we cannot invert it. However, what we can do is we can pre-multiply everything by x transpose. And now x transpose x, of course, that in and of itself is a square matrix. So long as x is not rank deficient, so as long as it has full column rank. And under that caveat, then we can invert x transpose x, and so we can put it on the other side, and now we have our full expression of beta, which you might know as the beta waltz, which is x transpose x inverse x transpose y. And now you will never forget this formula ever again. And of course, you can derive the formula for the variance of the estimator.